In our last video, we learned about the 4 different modes of natural radioactive decay. We learned that nuclei will either undergo beta particle emission, positron emission, electron capture, or alpha particle emission in their attempt to become a more stable nucleus. Today, we're going to use these radioactive decay reactions in a practical application called radioactive dating, which is basically a way of figuring out how old something is. If you've ever wondered how we figure out how old a mummy is, or how old an artifact is, or maybe a fossil, this is how we do it. What I haven't told you about radioactive decay is that some of these processes are really fast and some are really slow, and it just depends on the nucleus that's decaying. We have a way of comparing all these different rates of reaction by measuring something called the half-life of the decay. And the half-life is just a measure of how long it takes for half of your sample to decay. So it's the time it takes for half of the sample to decay. So for example, let's look at carbon-14. Carbon-14 is unstable. It will emit a beta particle and turn into stable nitrogen-14. And you might remember in the last video that I referred to the carbon-14 as the parent isotope, and the nitrogen-14 is the daughter isotope. So the half-life of this reaction, which we represent with a T and then a little 1/2 subscript, in this case, it happens to be 5,730 years. So what that means is that in 5,730 years, half of that original parent isotope will be gone and will have turned into nitrogen-14. Another example is uranium-238. Uranium-238, in fact, all forms of uranium are unstable. This one happens to do an alpha particle emission and turn into thorium. Turns out thorium is also unstable, so it will decay into something else. There's a long process here of many decays. But this first reaction has a half-life of 4.5 billion years. That's a long half-life, but it means it takes 4.5 billion years for half of this parent uranium-238 to disappear and turn into thorium. And here's one last example, oxygen-21. Oxygen-21 will decay into fluorine-21, and this happens rather quickly. This has a half-life of only 3 seconds. Now, if one of these radioactive isotopes happens to be trapped inside a rock or a fossil or a bone, then we can use its half-life and we can measure how much of that radioactive element is present, and we can use that information to calculate the age of that object. Here's a good video explaining how this works with carbon-14 dating.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
The video explained to us how the amount of carbon-14 in a sample can be used to date that sample. It also mentioned that substances with longer half-lives can be used to date older objects. So uranium-238 with a half-life of 4.5 billion years is often used to date much older objects. We're now going to try a simulation where you get to practice using the amounts of these different isotopes to date the age of an object. To run this simulation, you're going to go to the website listed on your lab handout, and this is called the Radioactive Dating Game. So you're just going to click a button to download it. And it's a Java-based applet. It'll run on most Macs and PCs. You might get a question asking whether you want to run it or not, and you can just say keep. And then when it's finished downloading, you can open this up and play it. This is what the simulation looks like when you open it. There are a couple different tabs. You can look at the half-life of individual atoms. You can look at the decay rates of carbon-14 and uranium-238. I'm going to start on this third tab with measurement. So the way this works is there is a probe here, and that you can select if you want to measure the amount of carbon-14 in a sample or the amount of uranium-238. You can measure the amount on an object or just in the air if you want. I'm going to leave it set to object and carbon-14, and the object that I have here is trees. So I'm going to plant a tree, and you'll just see what happens. As the probe is measuring the amount of carbon-14, you notice it's straight. Right up until the point that the tree died, the amount of carbon-14 in that tree was constant because it was being replenished by the carbon-14 that was being produced in the air. And there's a whole carbon cycle. So it wasn't until the point that it died that the clock started. That's when the carbon-14 started decaying and not getting replaced. And you can see that over time, less and less and less of that carbon-14 is present. If I pause the video right now, we're at 36.3% of the carbon is left, and we could use the numbers on the graph to figure out the age of that tree. So this is a way of estimating the age of something that was once alive. If I reset and switch now to the uranium, uranium has a much longer half-life, so that's going to be better at measuring the age of much older things like rocks. How do rocks form? They form from a volcanic eruption. So I'm going to click on erupt volcano. There's lots of lava coming out of this volcano. Eventually that lava is going to cool down and form into a rock. And when that rock forms, the uranium-238 that's in that rock begins to undergo radioactive decay. It turns into thorium, which then eventually decays into other things. But you can see from the graph that there's, just like with the carbon-14, there's this downward slope in the percentage of uranium that's still left in the sample. And so I'll pause this one. So again, if we know the percentage of uranium that's left in our sample, then we can look at a graph like this and we can just read off and figure out how old that rock is. Or what that means is, when did that rock form? When did that lava harden and turn into that rock? So you can play around with this screen if you want. It's kind of fun to use, but what you're going to spend most of your time on for this lab is the dating game tab. So here you have a whole bunch of objects. They're all buried in different layers in the ground. And you have your probe here. You can stick this to any object you want. I'm going to do the dead tree again. And when I see a box up here, it's going to ask me to estimate the age of the tree. Well, I'm not going to just guess at it. I'm going to do this carbon-14 dating. Now, I could try doing uranium dating on the tree, but see how it says 0%? That means that there's no uranium-238 in the tree to measure, so I'm not going to get accurate measurements using that kind of probe. I have to actually measure the amount of carbon-14 isotopes. And it's telling me that 97.4% of the original carbon-14 is still present in that dead tree. So now I want to look at my graph, and I want to find 97.4%. which would be somewhere around here, and then I want to read off what it is on the x-axis. Now this graph is not easy to read, but what makes it easier is you grab the green arrow and you line this up until you get to the percentage you want. So I was looking for a carbon-14 percentage of 97.4. I'm going to slide this over until I get as close as I can. Right there's 97.4. And so I'm getting that the age of this dead tree would be 204 years. So that's what I would type in the box. I can check my estimate. You don't have to be dead on with the number of years. If you get at least 2 sig figs in your answer, it usually accepts that as a good estimate of the age of the tree. If you go to measure a different object, like say I go to this rock down here, and I notice that the carbon-14 percentage is 0%, it either means that there's no carbon in that rock or that the rock is so old that all of the carbon-14 is now gone. And so that means you have to pick a different probe. You have to try uranium-238, or you can do a custom one. The custom ones don't have names, but you can select the half-life of that radioactive isotope. Okay, so go ahead and follow the rest of the instructions on the lab sheet and figure out the ages of a lot of these objects.